The next topic, magnetically coupled circuits. To analyze magnetically coupled circuits, that is, the interconnected loops of an electrical network through magnetic fields, we need to understand the concept of inductance, as the inductance is the property of material by virtue of which it opposes any change of magnitude or direction of electrical current passing through the conductor. The unit of inductance being Henry, it is given by Faraday's law of electromagnetic induction. A wire of finite length, when twisted into a coil, it becomes simplest inductor. As soon as the current will flow through the coil or the inductor, an electromagnetic field is formed. However, when any change of flow of direction of the current, the magnitude of electromagnetic field changes. This change of field induces a voltage V across the coil. Or in simple terms, we can say that when a current changes in a circuit, the magnetic flux linking the same circuit changes, and vice versa. An EMF is induced in the circuit. This induced EMF is proportional to the rate of change of current. That is, induced EMF V equals to L di by dt. Where V is the induced EMF, di by dt is the rate of change of current, L is the proportionality constant called self-inductance, and units are Henry. From the concepts of basic electrical engineering, the inductance is given by L equals to N phi by I, where N is the number of turns of the coil and that phi is the flux linkage. Let it be 1 and 2. Then from 2, I equals to N phi by L. Now substitute this in equation number 1. Then you'll be getting V equals to L d N phi by L divided by dt. From which V equals to L d phi by dt, N by L will be getting N d phi by dt. This is our V. That is equation number 3. Now, comparing equation 1, we can say that L di by dt equals to N d phi by dt. Then from which L equals to N d phi by di. Equation number 4. Here it gives the relation between magnetic flux as well as the current. This represents the magnitude of self-inductance. If the circuit consists of only one coil, then that belongs to the self-inductance, whereas we have two coils carrying a current I1 as well as I2. Each coil will have the flux linkage, that is phi 11 belongs to the self-flux of the coil 1, phi 22 belongs to self-flux of the coil 2, as well as there is a mutual flux, that is phi 21 as well as phi 12. The flux of coil 2 links with the flux of coil 1. That means it is phi 21. The flux of coil 1 links with coil 2 is known as phi 12. The induced voltage in coil 2, VL2, is given by the number of turns in coil 2, that is N2, multiplied by D, the flux in coil 1 linked with the coil 2, divided by the time dt. Let it be equation 5. Since phi 12 is related to the current of the coil 1 and its induced voltage is proportional to the rate of change of the current I1. So, V L2 is given by mutual inductance M of d I1 by dt. This is equation number 6, where M is the proportionality constant known as mutual inductance. Now comparing these two, M d I1 by dt equals to N2 d phi 12 by dt. Now from which M is given by N2 d phi 12 by d I1. That is equation number 7. Similarly, the voltage induced in the coil 1 is given by the number of turns in the coil 1 multiplied by d, flux linked to coil 1 from the coil 2, d21 divided by dt. The induced voltage is equals to the mutual inductance multiplied by the current here is due to I2, as d phi 2 is the flux in the coil 2 which linked with the coil 1. So d I2 by dt. Equating them, and finally we'll be getting M equals to the number of turns in the coil 1 multiplied by d phi 21 by d I2. Let it be equation number 8. When the coils are linked with air medium, the flux and the currents are linearly related, and the expression of mutual inductance are modified as this one, M equals to N2 phi12 by I1. Let it be A. Here M equals to N1 phi21 divided by I2. Let this be B. It may be observed that the mutual inductance M is the bilateral property of the linked coils. Coefficient of coupling is defined as the fraction of total flux that links the coils, and which is denoted by the letter K equals to phi12 by phi1, which equals to phi21 by phi2. Since phi12 is less than phi1 and phi21 is less than phi2, hence the maximum value of K is unity. Now multiplying the equations A and B, we'll be getting M square equals to N1 into phi21 phi12 divided by I1 I2. That equals to N1 N2. From this, phi12 equals to K into phi1, K into phi2 here, divided by I1 I2. That equals to K square. You can write N1 phi1 divided by I1, N2 phi2 divided by I2, which is nothing but the self-inductances. So K square of L1 L2. Therefore M is given by K square root of L1 L2, where K is the coefficient of coupling. Example, two coupled coils have self-inductance of L1 and L2. The coefficient of coupling K equals to 0.758. Find the voltage of the second coil having the number of turns 500 and circuit current I1 equals to 2 sin 314. Now given L1 equals to 10 millihenries, L2 equals to 20 millihenries, then mutual inductance M is given by K and the square root of L1 L2, and K also given, that is 0.75. Now substitute those values. 0.75 square root of 10 multiplied by 10 to the power minus 3, 20 multiplied by 10 to the power of minus 3. We'll get M equals to 10.6 into 10 to the power of minus 3 henries, or 10.6 millihenries. Voltage of second coil VL2, which is given by M d I1 by dt, that equals to 10.6 10 to the power of minus 3 derivative of current I, that is 2 sin 314t, that is given by 10.6 into 10 to the power of minus 3, 2 multiplied by 314 of cos 314t. When you calculate this, you are going to get VL2 equals to 6.66 cos 314t volts.